In this video, we're going to look at how we can do projectile motion inside of Inventor. It's actually going to be the same simulation that you saw that we did in the spreadsheet, which was basically vertical motion. So what we'll do here is we're going to go New and open up an assembly. Okay, you've completed the pendulum simulation. We're going to use the same parts here. We're going to place two of those links. Okay, so here's our first link. Okay, I drop that link down, and then I put a second one down. Right-click and say OK. One is going to be our base, basically something that's not moving. So to do that, we select it, right-click, and select Grounded. Next thing we're going to do is we're going to constrain this so that it will slide along this face to be able to work on there. So using constraints, I'm going to use the Mate command, which is the first icon here, one on the left. I'm going to select the front of our stationary with the back of the other piece. Okay, I hit apply. That keeps me in this command, so I can then do a flush command, which will keep the two sides done. When I press OK, it closes it. If I grab the first part, you'll notice it can slide up and down. Okay, so what we're going to do is we're going to set this up so that it's kind of lined up with the tops are matching. Get that as close as possible. Let's save this. We're going to call it Projectile. Okay, assembly. I had this before, so I'm going to overwrite that. Now that we've saved the assembly, we're going to switch the environment, go to Dynamic Simulation, and not watch their tutorial. And from here, you'll notice the system automatically interpreted the constraints and put in a prismatic joint. That's a sliding joint, basically, that's going on here. So the system on interpretation, when bringing it in, put the joints needed for the simulation. Simulation joints and constraints are related. Okay, we're going to turn on gravity by double-clicking on gravity, clicking on the back edge, get a line, and gravity is going up, so we're going to switch the direction to make it go down. Press OK here. We're going to add a trace so that we can see the path, and it'll be easy to be able to go and then identify the coordinates of it. So let's go to Trace, and I'm going to click right here in the center of that circle, and the reference I want to do so that I get it the way I want is I'm going to say New, and it's asking for the origin. So I'm going to pick a corner right here, and then the x-axis, I'm going to select the x-axis, a line that's coming forward. Next it wants the y-axis, so I'm going to click the y. So now x is going this way, y is going up. This way when I look at my coordinates, I know I want the y direction to be able to work on that. So I press OK. Okay, I want to do trajectory and velocity. So press OK here. Oh, let me change my trace color. I prefer the bright green when it's going. So I press OK here. Our next thing is, this is going to be treated as our 0 location. Okay, basically it's going off the ground, but we had to add that 9.8 initial velocity. So I'm going to double click on the prismatic joint here, and where it says degree of freedom, you click on that tab, DOF1, turn off computed, and put in 9.8 space m/s for meters per second. Now you'll notice it's pointing, it's saying positive is up, so because this is pointing up, that would be great. If you put it in and you see the arrow is pointing down, you'd put in a negative 9.8 to make this work. So let's press OK. This is how we've assigned the initial conditions. Now if from our previous analysis we knew that this process is going to take 2 seconds, so I'm going to change this to 2 seconds. Okay, click over here and then hit the play button, and you can see our part flies off and it comes back down. Okay, and we're finished with the simulation. If we zoom out, we can see the path here. Let's reset it and play, and you can watch the part going up and coming down. Now, incidentally, okay, I'm going to rewind this. Okay, we can look at our output grapher now and select our trace. Okay, look at our positions. We know it was our y position, and there is that parabola that we would expect to see in this. Okay, so we can actually look here. We can also pull down And remember all those time steps? Well, here it is. It's doing 0.01 delta t's. It's picking that up. And we're seeing that it's hitting the ground between 1.99 and 2.00 seconds. Now, should we wish to control the resolution of this, say we wanted more steps to be able to work in here, let me go minimize that. We can come over here, reset this, and we can say for 2 seconds we might want to do 1,000 time steps. Click on that, hit play, and now what's happening is it's doing a much finer time step. So when you give it the duration followed by the number of steps, you are in fact controlling your delta t by putting these two numbers in. So total duration versus time step. Now that this is finished, let's take a look at our output graph for now. Okay. And we have our trace, our positions. Here's our Y position. We've got that. Let's pull this out and now take a look at what our timing looks like here. There's a lot more points, but you'll notice we're getting our simulation at 1.996 to 1.998 is basically where it's coming in and it's crossing. Remember, this is a numerical simulation. It's typically not going to give you the exact answer, but as you adjust your timing, you can see we are within 0.002 seconds of the actual time that it should be to be able to do this. So this shows you how numerical simulation can give you some approximate answers. So when you're looking at something, you can get a feeling for things you don't have specific answers for. That concludes this video on projectile motion.